Welcome, Professor Manaswita. She is a faculty member at the IIT Bombay, and she's also a co-principal investigator of the open foam vertical of the FOSSEE project. And she has been associated with our team since long. She every year she guides our semester interns and summer fellows, and she's a wonderful teacher, which you will experience just now. Okay, so with that, I hand it over to you, Professor Bose. You can take it forward.
So let us start. We will start with this application of multiphase flow and gas solid, and with specific system that we will have for references, gas solid systems. Okay. So over the last 3-4 days, you would have definitely understood what is open source, why you should use open source software, and what is open source software. So why open source software? It is for flexibility, and learning is much better if we use open source software, and accessibility. Wherever we are, we can access the software. So these are the three main reasons why we should use open source software, right? Okay. Now, if we move to the next slide, see, we have I have organized this session into 4 modules. First, we will start with an introduction. We'll give some examples, and then basic concepts and terminologies, and the modeling methodology, and then we will couple with the CFD. So see, this methodology has 2 parts. One is the discrete element method, and we will see how do we implement an open source software, and then we will couple it with the CFD. Now, when we start with the overview, I thought of presenting this phase diagram, okay, to begin with, and tell you what we mean by multiphase flow at the very first place, because that's a wide area, and then from there we will move to the gas solid system, right? So what do we see on this figure? What are the 3 axes we see on this figure? We see on one axis we see some Greek letter phi with a subscript v. On the other axis we see one ratio dp by eta, and then on the third axis we see another ratio rho p by rho f. So what do they mean? So phi v is volume fraction. Volume fraction of what? Volume fraction of the solid. That is the fraction of the total volume occupied by the solid. Now, here, let's see if you can see something, and we can do some experiment. So, suppose if you can see this particular beaker here, can you see? Is the camera visible? Because I can't see much now with this slide. Can you see this beaker? Is it visible?
Yes, ma'am.
Okay. So, what would be the rough volume of this beaker? Any idea?
1 liter.
Okay.
Maybe 200 ml.
Okay. So suppose if we measure it. So this is a scale. And if we put it on this scale, I get to see that its diameter is roughly about say 40 mm. I'm taking a very rough measurement. Okay. So its diameter is roughly about 40 mm, and its height, it's roughly about, so its height is roughly about, again, I'll just measure the height. Its height, the graduation, each graduation is roughly about 10 mm. So it's about 50 mm. Okay. So what is the volume?
150, about 150 ml.
Some ml. Right, we can calculate the exact number, pi by 4d square into h, we can calculate that number, right? Now, I have some marbles here, right? I have some marbles here. Now, suppose if I put the marbles and I fill it in. I put the marbles and I fill it in. Roughly, I fill it up to this, whatever is the height that I have measured. So now you see, when you have filled this, okay, now I think, I'll not try to do these experiments because it's slightly difficult to show. But now you see, when you have filled this beaker with these marbles, whatever you could see or whatever you can imagine, that the entire volume did not get filled with the marbles, right? There is some voidage in between. Is that right? So the volume occupied by this solid divided by the total volume, in other words, the fraction of the volume occupied by the solid is the volume fraction, and that forms this particular axis. Okay, this phi v. Then the vertical axis, rho p by rho f, is the density ratio. And then what is the third axis? dp by eta. dp is the particle diameter and eta is the Kolmogorov length scale. So to begin with, I just leave it at saying that this is the length scale which is associated with turbulence. Now, based on this, you can see the nature of the flow that one get to see. The nature of the flow you have. You have granular flow here. Granular flow meaning it's the flow of the particles without where you don't have to account for the effect of the interstitial fluid. You have suspension rheology, where the effect of the interstitial fluid is very important, and you have one-way coupling, where you don't have to worry about the particles affecting the fluid flow. You have inertial clustering, preferential clustering. You have tracer particles, where you introduce tracers to understand the fluid flow behavior, and you have whole lot of other geometries. Here also you have something written as ST. What does ST mean? ST means Stokes number. So all of them we will be discussing in detail later, and we will see where the applications that we had talked about on this particular frame, in this plane, I would say in this three-dimensional space where they fall under. Okay, so this is one thing that this is very useful and we have to keep in mind. Now let us start with the next one, which is granular flow. Granular flow, if we formally define, it's a large collection of small particles. And what do we get to see here on this left side picture? What do we identify here? We have green moong, we have ragi, and we have tablets. In a sense, all of them are granular flow, and tablets are made of very fine powders, even they are granular. Okay, so in one simple phrase, granular flow is a large collection of small particles. And the second one is what makes the granular flow challenging or interesting is the collective behavior of the flow depends on the individual interactions. And what are the application domains? As the figure suggested, only a fraction of it, pharmaceutical and food. And other than that, what do we have? Agriculture, petroleum and petrochemicals, thermal power plant, and you name, wherever you can think of involving solid materials, tiny particulate materials, you have application of granular flow. In extraterrestrial phenomena, soil erosion. I mean, it's a truly multidisciplinary and interdisciplinary area. Now, long back, nearly 30 years back, there was an article which stated which stated that nearly 40% of the plant capacity is wasted due to the issues related to the handling of bulk solids. So this is known as bulk solid handling also in unit operations. Now, this scenario is not improved a lot even now. There are challenges. There are challenges in industries which need to handle large amount of bulk solids, though the empirical relations are, I mean, it's not that, the equipment don't work. They definitely work based on many empirical relationships, semi-empirical relationships, and a large amount of CFD DM simulations are being performed nowadays to understand it better. Okay. Now, unit operations involving the bulk solid flow, I have picked up two examples which are very widely used. One is fluidization and another is pneumatic transportation. And fluidization itself has a wide applications in coating, drying, polymerization, catalytic cracking, combustion, gasification, and many others. Okay, so keeping these applications in mind, now we move to the definition of these two systems. Now, I think, where I won't be able to play a file because it is being, the slides are being shown, slides are being shared, shown by somebody else. Wherever I don't have a GIF file, I won't be able to show something. But having said that, let us just go ahead with the definition. Now, suppose in fluidized bed, what happened? What is the definition? By definition, fluidization is a process whereby a bed of solid particles is transformed into something closely resembling to a liquid. This is achieved by pumping a fluid. This is a textbook definition. The textbook is by Gibilaro, and you can see this fluidization process that is happening in this particular video, where there are two different types of particles. The blue one is little larger particle than the gray particles, and air is injected from the bottom of the bed, and you see that there is a lot of bubbling kind of action at the top of the bed. So that is fluidization. Now, it is relatively a new technology. Now, what do we mean by new technology? Relatively new because it began in 1942. It's not very old technologies, like some of the technologies are centuries old, and this is going to be this is about 80 years old. What happens is, in fluidization, you see, let us look at this graph here. What is plotted here is delta P, that is pressure drop across the bed. So suppose we have one pressure at the bottom of the bed and another pressure point at the top of the bed, and if we just keep measuring the pressure drop between these 2 points, as we keep increasing the air velocity, then what happens? So as we keep increasing the air velocity, the pressure drop keeps increasing. So suppose when the air velocity was 2 centimeter per second, there was a corresponding pressure something around, say, 650 Pascal, and then kept increasing. Pressure drops kept on increasing, and then there was a point where pressure drop was high, and then within the error bar, pressure drop was almost constant. Okay. Now, why does this happen? And what does it have to do with fluidization? So at this point, where the pressure drop starts becoming constant, at this point, the buoyant weight of the bed gets equal to the, per unit area, gets equal to the pressure drop, okay, across the bed. And that point is known as the minimum. At whatever velocity that happens, that point is known as the minimum fluidization velocity. And after that, if you keep on increasing the velocity for a large value of velocity, the pressure drop remains constant. So that, and there bubbles form and all. that regime is known as fluidization regime. Different regimes of fluidization is there, but pressure drop remains constant. Now, what happens at that point? Buoyant weight is equal to the pressure drop is okay. That's fine. This is less than the terminal velocity of single particle terminal velocity. Minimum fluidization velocity is less than single particle terminal velocity. Okay, this is for multi-particle system, right? Now, why is fluidized bed attractive to technology? See, what happens is any rate processes, the rate of transfer depends also on the surface area available. And in case of fluidization, because the particles get dislodged from each other, the entire surface area is available for, say, whether it is heat transfer, whether it is mass transfer process. And that's why fluidization is, in some cases, it has shown remarkable success. And it is a promising technology. However, also we have to understand that the air flow rate is, or fluidization velocity is slightly higher than the packed bed. So there is always, there is always an optimization. Optimization always plays a role. So one has to work for every case. Pneumatic conveying system. Now let us imagine that we kept on increasing the velocity. Then what happens on a vertical pipe? Beyond the terminal velocity, somebody said terminal velocity, we will be defining those terms. Beyond the terminal velocity, beyond a certain point, if we keep on increasing the air velocity, then we have defined volume fraction. So volume fraction will become very, very small, and then the particles will start flowing, getting transported along with the fluid. Now that is vertically pneumatic transportation, vertical transportation. If we turn the pipe, 90 degree, so when it is vertically transported, see, we are on Earth, gravity is working in this configuration, gravity is working opposite to the airflow velocity direction. Now, if we turn the column 90 degree, then gravity will work normal to the mean flow direction. That is called horizontal pneumatic transport. Now, if there is horizontal pneumatic transport, then if we plot delta P versus superficial gas velocity, the same thing. The axis remains same, delta P versus superficial gas velocity. Here also the axis remains same, superficial gas velocity versus delta P versus pressure drop versus the superficial gas velocity. We get to see some curve with a minima. This minimum point is what is known as the saltation point in horizontal pneumatic transport literature. And beyond this saltation point, particles start getting deposited on the bottom of the wall, and that the deposition pattern looks like this tiny dune formation, a tiny dune kind of a structure, and that you can see from these figures. I do not know whether you can see it. If it is magnified, you can see this shape clearly, right? So now these are the two operations that mostly talked when we talk about gas solid systems. Of course, there are air jet mills and other things. Those are more complicated. I am not getting into this because they also have internals and other things, right? Now, before I get into the modeling thing, I'll talk a little bit about, this is for information, state-of-the-art experiments. One thing we see that, when we are in the dilute regime, so when we say dilute and dense, what do we mean? That if we have very low solid volume fraction, then we call dilute. So in this pneumatic transport line, let us see some places it is very dilute. We hardly get to see any solid particles. In those cases, we say this is optically transparent, so we can do some flow visualization experiments. But say in fluidized bed, within the bed or in the dune regime, where there is the solid volume fraction is very high, it is not optically transparent. We can't do any optical measurement. So for in those regimes, there are methods. X-ray tomography, positron emission, particle tracking, radioactive particle tracking, those kind of methods are used for experiments. And the detailed experiments we do it, or the data results of the detailed experiments that we have, it is good for the modelers or simulation people, because we have more data to compare our results with. We know whether the models we have used, they are sufficiently accurate or not. Okay. Now I'll give you a little bit of timeline about the modeling approaches. See, as we said, fluidization as a technology itself was developed sometime in 1940s. And during 1950s to 1960s, early 1970s, the approach was more phenomenological, empirical and semi-empirical based. Lot of experiments were performed during that time. Measurement of pressure drop and some visualization experiments using still camera, very nice experiments, and then correlating them. And the focus was looking at the pressure drop, minimum fluidization velocity, bubble velocity, and correlations for heat and mass transfer, like, correlating the Sherwood number with Reynolds number and Schmidt number, correlating the Nusselt number with Reynolds number and Prandtl number with different scenarios, compartmental modeling, and these kind of approaches. The continuum description of fluidized bed was proposed in 1960s, and that is the origin of two-fluid model. However, what was lacking at that point of time was a constitutive relation for the solid phase, and that was closed during 1980s, where kinetic theory of granular materials was proposed and developed. In 1990, CFD-DM was the work using CFD-DM began by Suji's group, and that paper is very well celebrated paper. Though DM for granular matter started way back, I think in 1979 by Kundal and Strack. And now CFD-DM is a very popular technique. DM itself is a very popular technique, and there's a lot of work that is going on is how to understand turbulence, how to understand the effect of particles on the turbulence, whether the presence of turbulence, whether the presence of particles enhance turbulence or attenuates turbulence, what kind of drag what is the effect that drag has, how to simulate large system, and more. Very recently, of course, people have started working on data driven modeling approaches also. Okay, so to cut things short, one can say that very broadly there are two approaches to model gas solid system. One is a continuum approach and one is a coupled continuum discrete description. In the continuum approach, both fluid and particle, both phases are assumed to be continuum, and there are constitutive relations. For fluid, the constitutive relations are known. Most of the cases, Newtonian fluids are assumed to be Newtonian. Of course, one can assume non-Newtonian fluids as well. And in case of coupled continuum discrete approach, the particles are assumed to be discrete or distinct element, and Newton's second law of motion, that is linear conservation of linear and angular momentum, are solved for individual particles. Coarse grain models are also there, and understanding about how coarse graining affect the macroscopic behavior is also a part of research. So this, it's a wide area that one can work on, and research is going on. Okay, so now getting to this background and the frequently used terms, voidage is what we have already, solid volume fraction is what we have already defined. Now voidage is 1 minus the solid volume fraction, right? So voidage plus the solid volume fraction, that has to be equal to 1. Solid volume fraction we have defined as the fraction of volume occupied by the solid. Voidage is 1 minus the solid volume fraction. Okay. Superficial gas velocity is the volumetric flow rate divided by the area in absence of any solid particle, right? So if there is no solid particle, whatever is going to be the velocity, that is known as the superficial gas velocity. Now sorry,
Ma'am,
yes.
can you start again from voidage?
Acha.
I just missed that part.
Yes. So solid volume fraction we defined as the fractional volume occupied by the solid divided fractional volume occupied by the solid, right? So that means solid volume fraction is volume of the solid divided by the total volume, right? Voidage is like, volume which is not occupied by the solid. So the way it will be written is total volume minus the volume occupied by the solid divided by the total volume. So this is going to be 1 minus volume occupied by the solid divided by the total volume. So that is going to be 1 minus solid volume fraction.
So it would be like the fluid volume fraction.
It is going to be the fluid volume fraction. So absolutely, it is going to be the fluid volume fraction. Now, suppose there is one question here, or one point here. Suppose there are multiple solids, say solid 1, solid 2, whatever. So it is going to be 1 minus summation of the solid volume fractions, right?
Yeah. Yes, ma'am.
Okay. Now, superficial gas velocity is the gas velocity divided when there is no particle. So gas velocity divided by the volumetric flow rate divided by the area, and area where the solid voidage is 1, that is the solid volume fraction is 0. Okay, there is no solid. There is no solid here, as if empty. You can see there are some red dots and there is some blank spot. So superficial gas velocity is Q by that blank area. Okay. That is the superficial gas velocity. So the local velocity is always going to be higher than the superficial gas velocity.
Yes, ma'am.
Right. Single particle terminal velocity is defined. Somebody wrote in the chat when I was defining the fluidization velocity. Somebody wrote in the chat saying that particle terminal velocity. So this is the difference. Single particle terminal velocity, when we do the force balance on a single particle, right? So what are the forces that are acting on the single particle? The buoyancy force, the body force, and the drag force. Now, if we balance them, we get the single particle terminal velocity as root over under root 4/3 CD. CD is the drag coefficient into rho s minus rho f by rho f into GDP. Okay, right? This is what we get as the single particle terminal velocity. Now, these are the terms that are very frequently used in the first 3 terms. In fact, are very frequently used in gas solid system. The 4th term, the minimum fluidization velocity, which we have already defined, is very specific to the fluidization problem. Suppose if you do a horizontal pneumatic horizontal transport, then the minimum fluidization velocity, or a vertical transport, or a downcomer, or a riser, then the minimum fluidization velocity is not important there. It is important only if you are working on a fluidization process, right? Now, this is one thing I just wanted to show, that whenever we do some simulations, we also have to look at the, validation, or how good our simulations is. Nowadays, mostly we are using packages. So, right, when we say that validation, it's not like earlier days where we are validating our codes, right? As what is it that we are validating? whether we have taken the proper grid is fine, whether the time step is fine, whether the accuracy or the convergence is fine. So we check the results against the experiments. And this is one result that is showing that, in one case we have simulated where we have measured the pressure drop in a fluidized bed and plotted against the superficial gas velocity, and that we have compared with the experimental value, and that results give us reasonable match, something within say 10%. Okay, this exercise it's a good exercise to do all the time whenever we are taking a simulation projects, right? Now, when we get into the drag, there are a couple of things to focus on, right? One thing to focus on is the drag force, it's a fluid solid exchange term, fluid solid interaction term. Now, drag force depends on the surface area to volume ratio, solid volume fraction, and the relative velocity, right? Now, see, most of the drag coefficient that we are aware of, that is mostly for the spherical particles or the cylindrical particles. They are already known. But for irregular particles, they are not known. So many a times we have to do resolved simulation if we are working with irregularly shaped particles. So all that we have to remember is that drag force depends on the surface area. So surface area to volume changes, we may have to use proper drag correlation. This is what we have to remember when we choose the drag force term. Now, when it comes to modeling particulate flow, see, mostly we are talking in terms of continuum and continuum discrete approach. So there is this one-way coupling, two-way coupling, and four-way coupling. So what do we mean by one-way coupling? One-way coupling is when particle moves in a fluid without affecting the fluid itself, right? So if there is a non-dimensional number which is known as the Stokes number, which is a ratio of two time scales. One time scale is the viscous time scale. One can get it again from the Stokes balancing the momentum conservation equations at equilibrium. One gets the momentum conservation equation for the particle, and from the time scale one gets the viscous time scale. And from Stokes drag law, if you look at the Stokes drag law, the viscous time scale is rho PdP square by 18 mu. And one takes the ratio with or one compares this viscous time scale with fluid time scale, which is L by U, and that is the Stokes number. So when Stokes number is very small, one can assume that the particle is not affecting the fluid flow. So it is one-way coupling. Fluid is affecting the particle flow, but particle is not affecting the fluid flow. Two-way coupling, when fluid and particle both affect each other, and four-way coupling when interparticle interactions are considered. So interparticle collisions are considered. If that is the case, then we say discrete element modeling, and four-way coupling is CFD DEM modeling. Okay, here we have shown two examples. One is fluidized bed and one is horizontal pneumatic transport. Then the next question comes is, what are we doing for the fluid phase? So there are two questions here, whether we are considering the fluid to be a Newtonian fluid. Number one, so suppose we say, yes, we keep it simple, we take it to be Newtonian fluid. Then the next question comes is, what kind of a turbulence modeling we are using? So are we going to use RANS, LES, DNS? And as we progressively going from RANS to LES to DNS, accuracy may be improving, or details, the details of data that we are getting, that may be increasing. However, at the same time, the time of computation is also increasing. Now, this is one of the first papers that came up with this CFD-DEM algorithm. Okay. Now, see the way it works. Once the algorithm starts, it's in a nutshell that I'll be telling you. Once the simulation starts, within one fluid time step, there are multiple particle time steps. That's all we have to remember. Within one fluid time step, so within the time step, suppose within one delta time step, fluid has advanced by one delta time step. Within that, particle has advanced by several time steps. So that ratio, what is the ratio? In fact, if you do open form and all, I think you have to define also that ratio. So and that ratio is always more than 1. I think people keep it's something around 10. Now I will get into the discrete element method, because that is what we have been talking about, the discrete element one. So in discrete element method, what we do is we solve the linear and that is the first equation, and the angular momentum conservation, that is the second equation for individual particle. So the first equation says that rate of change of linear momentum is the sum of the forces acting on it, and the second equation says that rate of change of angular momentum is the sum of the torques acting on it. So that's it. And I is the ith particle, j is the jth particle. So now how do you go? If ij is the forces applied on ith particle by jth particle, all jth particle in contact with the ith particle, and the torque is the similar way. And Pw is force applied on the particle, ith particle by the wall, gravity, drag, and buoyancy. One can also consider lift. I haven't included the discussion of lift in this presentation. So here you see, when we are talking about the start with the wall particle situation, see, we can have perfectly smooth wall or we can have rough wall. And if we have the perfectly smooth wall and I mean, this is not a perfectly rough wall, in general rough wall, the way the collision happens, that looks different. See, one case it is a perfectly specular collision. The way, what we mean by a perfectly specular collision is the incident angle is same as the reflected angle, and the rough collision is more like a diffuse reflection, diffuse collision. Okay, and that you can see that you can have rough wall by embedded particles, that will give you a diffuse collision. Now in DM, which is also like a soft sphere model, what does it mean? It means that at the contact, when two particles are contacting, they can deform. Okay, so that means one can put a spring between two particles, and under the force, under the load, the spring compresses. That is how it is modeled. Now, if it is just a spring, then the contact will be elastic. There has to be some dissipation. So a dashpot is also added. This is known as a spring dashpot model. If the spring is linear, then this is a linear spring dashpot model. One can put this linear spring dashpot model to determine the normal force. They can use to determine the tangential force as well. So what are the parameters that we have to define here? To determine the normal force, we have to define the spring stiffness constant and this viscous dissipation coefficient. Okay. Now let us understand the meaning of it. So suppose if the spring stiffness constant is very high, what does it mean? If the spring stiffness constant is very high, it essentially means that particles are less deformable. If they're very, very hard particle, when is it less deformable? If they're very hard particle. And hard to deform. Yes. And what is the physical interpretation of the viscous dissipation coefficient? See, if we take this marble, again, I wouldn't try to show this experiment, but suppose if we take this marble, imagine that you all played with this marble. Suppose if you take this marble and you drop it on the floor or the table, the height that which you have dropped it, will it come back to the same height?
No.
No. Why not?
Because there is energy loss.
Yes, absolutely. Because and that energy loss, we'll say that it is inelasticity, right? So now this viscous dissipation coefficient will be related to inelasticity. Now inelasticity is which is experimentally measurable. If you can relate the viscous dissipation coefficient to inelasticity, you can always adjust this parameter, right? Done. Well, how do we get KT? That is a spring which we have put in the tangential direction to get the tangential coefficient of restriction. Sorry, not tangential coefficient. I'm sorry. The tangential spring stiffness constant. First of all, why should I have a normal force and the tangential force? When is tangential force important? Suppose you have a perfectly smooth surface. If you have a perfectly smooth surface, then what is going to happen to the tangential force? With the video that we have seen, absolutely. So then we don't have to worry about KT and mu and all these things, because friction coefficient is 0, right? So now suppose if there is surface roughness, then we have to worry about the tangential. We have to worry about this tangential force, and then we have to worry about this KT. So how do we decide what is KT going to be? See, in case of linear spring dashpot, there could be multiple ways that you could do it. It is arbitrary choice. You could have, like, because these are two springs, you could equate their time periods for normal, and by equating their time periods, you get one ratio. You could also look at other things. You can look at a little bit of other models, that Hart's model and all, and from the compliances, if we can start defining this spring stiffness constant as an inverse of compliance, from there we can get some ratio, and we can see the effect of them on the final result, and then decide what we should define as the ratio of KT by Kn. Okay, eta T, which is inelasticity, which is related to inelasticity for the tangential spring, it is normally set to 0, and mu is the friction coefficient. And again, this is like, this is a measurable parameter. This is a listed for material, so you can choose whatever value you would like to choose for the simulations that you are performing. Now, this is for your information or knowledge that, as I said, DM started for granular material is in 1979, and it is going strong and stronger. There's a lot of development, and I have only highlighted the key papers. You can make a note of it, or some numbers, of course, I think I did not update it, but that citation numbers I did not update. These numbers is going to be different. But what does it say? That Kundal and Struck in 1979, they are the first one to employ the linear spring dashpot model to simulate dense granular system, and their work is actually in soil mechanics, and they kept the tangential to normal spring stiffness constant as two numbers, 2/3 and 1, and that complies with the definition of spring stiffness constant as inverse of the compliances. Now, Suji and co-worker, they use nonlinear spring. You can also use nonlinear spring. You don't have to you have not necessarily that you have to use linear spring. Silbert and co-workers, they used both linear and the nonlinear spring. They used the ratio of KT by Kn as 2/7. They set the way they have come to this number is by setting both time periods equal. And after that, there have been plenty of work for implementing these contact laws for large scale simulations, different force displacement, to understand force displacement behavior, force grain model, non-spherical particles, cohesive particles, and different geometries with internals and all other work. Okay, I'll skip this for the time being, but all I'm trying to say that nonlinear model, when you are applying nonlinear model, if at all you are choosing nonlinear model in the sense nonlinear spring, what I mean is nonlinear spring. If you are choosing nonlinear spring, you have to be little careful about what you are choosing, And I would always say that if you're doing it for the first time, please start with 2 particles or 1 particle and a wall, see how they're behaving, set the parameters, and then go ahead with the large scale simulations. Okay. This is just to give an idea, how popular these methods are, and this is a list of some of the software that I am aware of. There could be many other software. It's not like all. The some of the software that I am aware of is LAMP, Slides, MFix. These are the 3 software that I am aware of. Okay. Now coming to the end of this, again I'm reminding that in DEM, when we come to this end of the contact law, first one we have only discussed about the first force, that is Fij. Use the spring and the dashpot. And the second one also, in that case, 1 particle will be replaced by the flat wall. Gravity, of course, we know. Then we are left with drag force, and we will get into that discussion soon. Now go to the next slide, please. Before we get into the drag force, I'll show you some of the results which will give you an idea how critical it is to choose the parameters properly. Okay, and this is what I was trying to tell you, that eta n, that is a viscous dissipation coefficient, is related to En, and you can see that the relation. It is an analytical solution, and typical En values are 0.7 to 0.9. These are the values, but so here, I'll show you a simple system where a collection of particles is energized by subjecting them to a vibrating wall, and then imagine that these blue particles are moving around with random velocities, and we have simulated them using spring dashpot model with En ranging between 0.7 to 0.9 or 0.95, and we set eta accordingly, that is a viscous dissipation coefficient accordingly, and we have used 2 or 3 different combinations ratios of Kt by Kn. And what we have seen, and different values of friction coefficient, and what we have seen is, this is more about the problem itself, so I will skip this. I'll have more discussion towards the end. Go to the next slide, please. This is how you set up the problem in LAMPs, so one can explore. So I will again not go through it in detail, but you can see that you set up the units, you set up the atom type, which is sphere, dimensions, boundary, initialization, arrange the particles, set up the contact. You have to choose the pair style granular, pair coefficient. This is linear, so hook spring, and then we put all the other numbers. Here we have put KT 2 by 7 of Kn, printing position, time step. So this is the script, and then we download the executable from Windows. If you want to install LAMPs, we do the post processing. We need to do some of the post processing to get after doing this DM simulation, all we get is position and position, linear velocity, and angular velocity as a function of time, and that is every time step, in the sense every writing time step. Now from there, what we can get a lot of information. And what are the information that we can get? See, what are the informations that we can get? We can get, we can calculate this, what we know, tell us the En is what we have supplied. What we can get is beta. Beta is rotational coefficient of restitution, that is a ratio of the post to pre slip velocities. And what the another important thing that we can get is the number of particles at contact at a given time, the frequency distribution of it. This we can get from the DM data. Now finally, what is it that I'm trying to show you? I'll skip some of the slides here. You can see that how the particle is contacting with the wall, how the particle is contacting among each other. This all we have picked up from the simulations. But now go ahead. I'll show you finally what this I'll skip. This is of course very specific to the problem that we have worked on. See, this is what I wanted to share with you. From this DEM, we have this number of, at every time step, we have the position, velocity, and angular velocity of the particle. So from there, we could get many information. What information we could find is the number of particles or the exact identity of the particles at contact. And when we got the identity of the particles at contact, we resolved their contact, and we found that depending on the choice of Kt by Kn, we get to completely different behavior. One gives us the blue line, that is 2/7. The other one, if we define the stiffness as inverse of compliance, gives us the green, red, and black line. 3 different values. Okay, they give us completely different functional behavior. Okay, so without getting into the problem itself, what I want to communicate here is the selection of parameters for the problems that we are solving is very, very important. Okay, now our choice has to be there. We have to be very clear which problem we are choosing and how we are selecting the parameters, right? And here I am going to take a pause before I get into the fluid-solid interaction. Do you have any question? If there are no questions, then I'll go ahead. I'll tell you something about the drag. See, these are the building blocks. Okay, so I'm focusing more on the building blocks. Rest, of course, it will come through working. So now we'll start with the fluid particle system. So, so here we have looked at the contact force, wall contact force, gravity, of course, we don't have to look at. Now we'll get into the fluid drag system. So if this is in fluid particle system, now effect of the interstitial fluid is to be modeled. Continuity and momentum conservation equation for the fluid phase needs to be solved along with the particle phase. So one of the ways we do it is open foam and lights, and they talk to each other through CFDM, right? So now how do we understand the fluid drag force? We have said that within every fluid time step, there are multiple particle time steps. So what do we mean by multiple particle time step? Now that we have gone through the DEM, so each particle time step, the DEM equations are solved. Once we have got the position, say after 10th time step, we have got the positions of the particles and velocities of the particles and the angular velocities of the particles. Now with that, we calculate the drag force at the fluid time step, right? This is what we are here calculating the, can you see this? On the right panel, there is calculation of the interparticle contact force. We are at that step. Now, how do we calculate interparticle drag force? So this is where I'm first showing you the fluid phase equation. Fluid phase equation as continuity equation, that is the first equation, and the second equation is the momentum conservation equation. This equation you must have seen several times over the last 3 days, so I'm not going to get into that. I'm going to talk about this F term, that is that interface exchange term, right? F has this beta into relative velocity, and beta is what given as 3/4 CD, which is the drag coefficient, into the gas velocity 1 minus 5 again the mod of the relative velocity divided by d, and 1 minus 5 to the power minus 2.65. This is which kind of a drag relationship I am using. This drag relationship is known as this is Gidas-Pauw's drag relationship. Okay, I am showing you only one drag relationship, right? Now, Gidas-Pauw's drag relationship blends a single particle approach and a multi-particle approach. So here I am showing you the single particle approach. What do I mean by that? Okay, let us start from the Stokes drag law. Because Stokes drag law, we have the analytical solution, right? If you recall that we showed you creeping flow, CD is equal to 24 by RE. single particle drag coefficient. Now, suppose if we want to correct it for inertia, you see this CD given here, 24 by RE into an inertial correction. Now, this is for a single particle where the streamlines haven't bent due to the presence of the other particle in the neighborhood, in the vicinity. Now, if there are particles which affect the streamlines, which bend the streamlines, then there has to be a volume fraction correction. So this volume fraction correction, one gets to see that 1 minus 5 to the power minus 2.65. This is called something like a Richardson-Zaki correction. Okay, so this is coming from the single particle approach, and I think this is also known in literature as see, this part is this CD is Schiller-Neumann drag law, and then this with the volume fraction correction, I think this is Venue drag law. These names may be slightly confusing because similar. One has to look at the names very correctly, but I think this is popularly known as Venue drag law when you have the volume fraction correction included in it. Okay. However, the approach is from the single particle approach, a single particle limit, and that's why it is valid for phi s less than 0.2. Phi s meaning here the phi s represents solid volume fraction. So phi s, lowest phi s means what? Lower phi s means dilute regime. Phi is larger than 0.2, that comes from the packed bed regime. Here, the expression that is derived for beta comes from the Ergun equation, which is a combination of Blake-Palmer and Kozeny-Karman equation. The first term represents, so that is the pressure drop equation in a packed bed, where the first term is for the viscous forces, first term where the viscous forces are dominating, and the second term where the inertial forces are dominating. Okay, now when you blend together, it is Gidas-Pau drag law. This is one of the drag laws. Now, there are multiple drag laws. There are actually many drag laws that one can choose and one can see the effect. But what is important is, how do we calculate the drag? See, in a CFD-DEM framework, typically the fluid grid is larger than the particle grid. Like, one fluid grid has multiple particles, at least 2 particles. So, the drag force on the particle is calculated with the fluid velocity interpolated at the particle center. Right, and that is how drag on the particle surface is calculated. Now, when the drag on the fluid is calculated in the same fluid volume, the drag force is again interpolated or summed back, averaged back on the fluid grid cell. So that one has to remember and typically 8 closest fluid grids are considered for each particle location for the interpolation. I mean, one can vary this number, one can see the accuracy and all, but there are 2 ways. Like if you are doing a 2-way coupling or a 4-way coupling, you have to keep in mind that first you have to calculate the drag force on the particle, and then you have to translate that drag force on the fluid grid. Okay, both things need to be performed. Here I have listed some of the drag forces. There can be many other drag forces. I mean, there are many other drag forces, and one has to refer to the literature for the drag forces. And with a open form or open source software kind of a framework, one can always add the drag force. One can modify the code to add drag forces and run the simulations. And these are the methods. Again, CFD-DEM simulation. The only one point is that OpenFOAM, I think even now it is compatible only with OpenFOAM 5, and that is a challenge. I think you can contact Saurav he's a PhD student who has submitted his thesis. He's waiting for his soon-to-be doctor. He has worked extensively on CFDM, and I think there may be others also who can help from FOSSEE group. Payal will be the contact person, and they will help you with installation. But the challenge is this, that it is still on OpenFOAM 5, as far as I know, but I think they will be, they are more familiar and more up to date with the installation. So there are the installation slides here. So here also, I just tell you before I go to the conclusion, very quickly, I want to tell you something, that when we were doing, this is Saurav's work, when we were doing this flow through horizontal channel, the quick tests that one needs to do is, whenever we expect the profiles to be symmetric, whether they're symmetric or not, whatever quantities we can measure through experiments, are they within the experimental error bar or not? Those kind of checks we need to perform when we are doing the simulation work. Okay, with that, I come to an end. Gas solid flow is important for industrial application. We could show only a couple of them, but there are many others. CFDM modeling is a state-of-the-art method, and with new computational facilities and this coarse graining thing, it is, one can really simulate large systems. OpenFOAM CFDM lights is an open option, is a very good option. DM parameters are very important, that we have seen that you get two different contact laws, but how it relates to the macroscopic behavior, we have to, we have to look at the system and tell. Drag correlation is important. Results can be different, need not be. And it is important, it is very, very important to analyze the results. So with that, I thank you all for your attention.
Thanks a lot, Professor Manasvita. So it's an honor to welcome you in this faculty development program. So thanks a lot for the informative session. And thanks to your students also, Mr. Saurabh. Thanks a lot.